In the last section, we looked at a model for a player with a 50% chance of making a basket on every shot. And we were able to get a handle on the number of runs of various lengths to expect in the data with some very elementary tools. The idea of an experiment, a sample space, and then we assign probabilities to the outcomes in the sample space using either logic or empirical evidence. Today we'd like to make a model for a player with a probability P of making a basket on every shot. And in order to do that, we need to introduce some new tools. In particular, we'd like to introduce the concept of an event and the intersection of events, conditional probability, and the concept of independence. We're often interested in the probability of an event, which is perhaps more complex than a single outcome in the sample space. And such an event will correspond to some sub-collection of outcomes in our sample space. So for example, if I roll a six-sided die and observe the number in the uppermost face, I might be interested in the event that the uppermost face shows an even number. That event occurs if either of the following three outcomes occur, a 2 or a 4 or a 6. So the event corresponds to a subset or a sub-collection of the outcomes, namely the one written at the bottom of the screen, 2, 4, and 6. An event is a subset or a sub-collection of the simple outcomes of our sample space S. And all subsets of the sample space describe an event, including the empty set, which describes the event that nothing happens, and the entire sample space itself, which describes the event that something happens. Events with a single simple outcome correspond to a simple outcome of the sample space. And given a verbal description of an event, the corresponding subset is given by all outcomes which fit that description. We usually give names to events which are capital letters, as shown on the bottom of your screen, A, B, C, D, etc. Here's an example. Suppose I roll a six-sided fair die and observe the number on the uppermost face. I've written the entire sample space here. And let's consider the event F, which is the event that we observe a number larger than 2. Which subset of the sample space does this correspond to? Well, I have to list all outcomes in the event. And we have 3, 4, 5, and 6 fit this verbal description. So therefore, F is that list, 3, 4, 5, and 6. What's the probability of an event? Well, to calculate the probability of the event, we list all possible outcomes in the event, and then we add the probability of the simple outcomes in the event. So, for example, if I roll the fair six-sided die and observe the number on the uppermost face, what's the probability that the number is odd? Well, let O be the event that the number is odd. Then O corresponds to the sublist 1, 3, and 5. And to calculate the probability of O, I add the probabilities of those three outcomes. So I get 3 times 1 over 6, or 3 over 6, which is 1/2, which is probably what you expected. If I roll a fair six-sided die twice and observe the number on the uppermost face for both rolls, then the list of possible outcomes is going to be a pair of numbers in the order in which they were observed. I get 36 outcomes in all in my sample space, and it's easy to believe that they're all equally likely because it's a fair die, and no one should be more probable than the other. So each outcome in the sample space has probability 1 over 36. Let E be the event that the numbers observed add to 7. What's the probability of E? Well, to find that, we list the simple outcomes in the event E and then calculate their probabilities and add them. Here I've highlighted the simple outcomes in E in red. It's just that off-diagonal element, the off-diagonal of the rectangle. And we have a list of the outcomes in E. We have 6 of them. And therefore, the probability of E is 6 times 1 over 36, which is 1 over 6. Now, you might have noticed something, that in an equally likely sample space, it's easy to calculate probabilities of events. If I roll a fair 6-sided die twice, what's the probability that the numbers add to 11? Well, I have 2 outcomes in that event, and the probability that the event happens is the sum of the probabilities of those 2 outcomes. So it's 2 times 1 over 36, or 1 over 18. By now you've probably guessed the formula for the probability of an event in an equally likely sample space. If I have an equally likely sample space, then every outcome, every simple outcome, has probability equal to 1 over the number of elements in the sample space, 1 over ns. And then the probability of an event A is the number of outcomes in A times 1 over ns, which is the number of outcomes in A over the total number of outcomes in the sample space.